remember, Uri was a postdoc here a few years ago, and now he moved a little bit up north in Cambridge, in Harvard, the Center for Mathematical Science.
Yeah.
Yeah. So thank you very much. We'll talk about what's written on the board.
Thank you, Massimo. It's great to be back at NYU. And thank you so much for having me. Today I want to tell you about critical phenomena that appears in the process of scattering of black holes. And here by black holes I mean Kerr black holes, so astrophysical, real-world black holes. This work is rooted in some discussions I had with Maria Rodriguez when she was on sabbatical at the Black Hole Initiative. And it's part of a larger program and collaboration with Alfredo Guevara. So we live in the Black Hole era. This is a catalog of the events that were detected by the LIGO Virgo-Kagra collaboration during the first 3 runs. So it shows about 100 events that were discovered between the years 2015 and 2020. Now, most of the events here are black holes, but there are also some that involve neutron stars. And this is a little bit outdated. Since then, last year, the collaboration released the results of the 4th run, which already doubled the number of events, of verified events, and there are a few more that are, as you can see here, that are preliminary. So what seems to be happening, or what we see here, is that the rate of discovery of detection, this is a graph of the cumulative number of detections, and what we see is that with every run, the slope increases here. So the number, the rate of discovery is really remarkable. Yeah, so for me that's saying that this is the future, at least of gravitational physics, but maybe even more broadly. Now, this is the future not only by extrapolating on the performance of this collaboration, but also because there are more experiments that are planned for the near, medium, and far future. LISA, the Space Observatory, Einstein telescope, which is an underground experiment, and for the farther future, Cosmic Explorer. So the future is promising, and there are more avenues for exploring black holes. For example, we've all seen the famous picture that was taken by the Event Horizon Telescope, a mission that we hope to be able to probe the photon ring. And in this case as well, there is a next generation experiment under planning. And for all of these reasons, Robert Dijkgraaf called the black hole the atom of the 21st century. So anyway, the message here is that the future of black holes is very promising, and we expect to have a lot of data, a lot of measurements, and we should prepare for that. In other words, we are witnessing the dawn of precision black hole physics, and I think I borrowed this phrase from one of Sergey's talk, but maybe Sergey also borrowed it from somewhere, I don't know. But anyway, it's the dawn of precision black hole physics, and in the era of precision measurements, there is a strong need for robust predictions. Okay, so that's the message. And I think that for this crowd, I don't need to do too much of convincing, but if there are any comments or questions at this point.
I thought that the atom analog was Lenin Susskind originally, the Dijkgraaf.
Yeah, okay, I don't mean to, yeah.
But I didn't borrow it. Just maybe somebody used it.
Okay, yeah. So this, So I credit this phrasing to Sergey, and yeah, I don't think I need to do too much convincing here. But yeah, the point is that there is strong need for robust predictions, and when I think about robust predictions, I think about symmetry breaking, and the reason is that symmetry breaking has proven to be an indispensable tool in almost all areas of physics. So yeah, again, I don't need to say much to this crowd about the importance of spontaneous symmetry breaking in QFT and particle physics, countless number of examples, the Higgs, for example, and so on. And perhaps the gold standard of this paradigm is actually in condensed matter, where people classify different materials and different models into different universality classes according to the phase diagram that they exhibit. Okay, I say that it's perhaps the gold standard because, well, at least in my opinion, conceptually, we would have liked to do something similar in QFT, but it's just too hard. QFT is obviously harder to solve than discrete systems. So in this case, we really have a very pleasing situation. And in cosmology, we can also think about symmetry breaking. So symmetry breaking was really is an indispensable tool that has been very fruitful in producing robust prediction. And the question that I want to raise is, what about black hole? One more thing that I want to say is that the mechanism in which the symmetry is broken in different cases is different, but the underlying paradigm is that in all of these cases, there are some perturbations that break an underlying symmetry. Okay, so perturbations that break some underlying symmetry, and the question that I want to raise now is, what about black hole perturbation theory? Okay? And yeah, I'm of course not the first one to think about that. Let me very briefly review what has been done, what appeared in the literature. And in general, I would like to classify the subject of emergent symmetries in black holes into two categories. The first one is emergent symmetries in some regions of space-time. Let me call it regional symmetries. So for example, emergent symmetry in some near horizon regions or near ring. And there are many, many works on the subject, and this is definitely not an exhaustive list. I just mentioned some of the works that are relevant here, but there are many, many important works. The second category of emergent symmetries are symmetries that emerges in some limits of the dynamical equation of the perturbation, or the wave equation, for example. And usually people discuss the limit of zero energy.
But that's a little bit hybrid, no? Because Castro-Maloney Strominger is a sort of...
No, this is... It's a symmetry of the wave equation in some limit, not of the...
No, the emergent conformity.
Of course, of course, the things are not unrelated, but there is a distinction. And more recently, it's been promoted by various groups, but one of the leading groups is here by Sergey and Misha and Charles Lambos that studied the zero or low energy behavior of the wave equation around Kerr, which is related to the tidal deformations and the low numbers. So what I'm going to show today is closer in spirit to this second category. In fact, I was inspired by this series of works, and one thing that I was looking for is to see whether there are some further implication of the symmetry and of the symmetry breaking. Namely, these hidden symmetries that appear at zero energy, they appear exactly at zero energy. But the question is whether there are some implications away from this point, away from zero energy, that are some constraints from the way in which the symmetry is broken.
Symmetry, energy of what?
Of the frequency of the perturbation. I will show exactly. In any case, what I want to say is that I didn't see it at zero energy, but I found it in a different place. So conceptually, it's similar to this, but not for zero energy. And yeah, I think when I show the results, it will be easier to discuss and compare to results in the literature. This first category is a little bit different, and I think it's a bit harder to connect this type of regional symmetries to experiments. because, well, we don't have direct access to the near horizontal region and so on. Any questions about this? Just to review briefly what has been done in the literature. And now what I want to discuss is the importance of black hole perturbation theory to experiments. So black hole perturbation theory captures a few important effects that we hope to measure. So first of all, in the process of compact binary coalescence, it captures tidal effects during the in-spiral phase of the merger. And it also captures the quasi-normal modes that control the ringdown phase, the decay of the waveform during the ringdown phase. Okay, so obviously it doesn't capture, black hole perturbation theory doesn't capture the full two-body problem, but it does capture these two important effects. In addition to that, in the Icona limit, it describes the photon ring. Okay, so those are some of the important events, some of the important effects that we hope to measure. Not everything, but some of them. So this is the observational or experimental importance. Any questions? Okay, let's move on, and let me briefly review what is black hole perturbation theory around Kerr black holes. So the Kerr metric was discovered in '63, and following its discovery, it has driven a huge effort in understanding the space-time and perturbations around it. And perhaps one of the most important works is by Tucholsky. So this is a screenshot. I took some screenshots from the original paper. This is a Kerr metric. And what Tucholsky found is a master equation that describes perturbations of different spins around the Kerr metric. So that's a very neat result because it describes different types of perturbations with different spin. Here S is the spin of the perturbation. And he put it into a very simple and neat form. But even more remarkably is the following feature. What Tucholsky found is that the perturbation takes this separable form that is written here. Now, the first two factors here, the dependence, the time dependence and the azimuthal dependence of the perturbation, the separability of them is trivial and is implied by the isometries of the background. However, the separability of these two factors, the radial component and the angular component, is not implied by the isometries. And in fact, we don't know what's the reason for this. It didn't have to be this way. It's true, but it's not clear why it is this way. No one knows. I think that there might be a principle behind it that we still don't understand, but it's an open problem that I will not address today. But in any case, this simplification or this separability simplifies the problem a lot, because otherwise the two equations would not be separable and it would be much harder. So the Tucholsky equation separates into two, the radial and the angular components, and they are solved using the method of separation of variables. They share a separation constant, A. Here it's called A, and lambda is related to it. Again, the equation depends on the spin of the perturbation. And yeah, so that's what I wanted to say about the Tucholsky equation. I know some people in the audience are experts on that, but for people that haven't worked on this topic, any questions?
Now, what is T? Is it, you say the vacuum case T equal to 0, but
yeah, well, I just took some screenshots from. This is just perturbations around Kerr.
no. But what is this parameter T?
I don't remember the paper by heart, but
certainly it's not the temperature because AR.
Yeah, it's not the temperature of the black hole. Forget about it. It's just a question for perturbation around the Kerr metric. It's just a screenshot of part of the paper, so I don't remember what it refers to exactly. Maybe it's a stress tensor. I don't know. Any more questions?
So how exactly? So this object psi, how exactly does that relate to? Why is it, also what are we? Are we perturbing the metric? Are we?
Yeah, it's perturbation around the metric.
Okay. But psi is a scalar field. How do we get from psi to a perturbation of the metric? How do we get from psi to a perturbation of the metric? Is psi like?
That's a good question. That's a good question. Yeah, that's. It's actually it's not a perturbation of all the components of the metric.
Okay.
It's only the component of the field that is the long range.
Okay.
So this is done using a method called the Newman-Penrose formalism, in which the different gravitational, the different components of the metric are described using 5 complex scalars, so 10 degrees of freedom, and that describes only the one that decays the slowest and remains only the radiative part. So that's a very good point. It doesn't describe all the gravitational degrees of freedom.
Okay, but psi is some complex linear combination of components of the metric or some decomposition thereof. And
Yeah.
Okay.
It's analog to psi is for the gravitational case it's analog to the far field, how it's called, far region, far field component of the electromagnetic field.
Okay.
And the same for electromagnetic perturbations. It will only capture the radiative degrees of freedom. That's a very good question. Any more questions? But I want to emphasize that this is the component that is relevant for experiments, because at the end that's the component that we measure.
Because we are far from the black hole.
Exactly. Any more questions? Okay. So despite the separability simplifies the problem a lot, but it is still hard to solve. And the reason is that the Tucholsky equation, both the radial and the angular, are ODEs with 4 regular singular points. These equations are called the Owen equations, and there are no closed form solutions. So of course we can solve it numerically, and there are many works on addressing this problem numerically. But what I want to argue today is that, well, numerics are very important, but numerics alone are not enough, and I want to understand more qualitative features of the phase space of solutions. Okay?
Can I ask you something?
Yeah.
So the Cohen differential equation is in some coincident point becomes like similar to the hypersymmetric.
Yeah, I'll
So in
discuss that.
some part of the parameter space it should be.
Yeah, that's exactly what I'm going to talk about. I'm going to use this feature. Okay, so and I want to improve the qualitative understanding in the spirit of symmetry breaking. Now, symmetry breaking is a synonym for collective phenomena, and the collective phenomena that takes place in this problem is called black hole superradiance. Black hole superradiance is the phenomena of a spontaneous amplification of a wave that is scattered from the rotating black hole, and if the frequency of the wave lies within this range, then the scattered wave will be amplified. Okay, so this range is defined by here. Lowercase m is the azimuthal number of the perturbation, and omega h is the angular velocity of the horizon. And the statement is that if the frequency of the wave lies within this range, the scattered wave will be amplified. That was discussed by Zeldovich in '71 in a more general context, not just for black holes, but for general rotating bodies. And soon after, it was studied for the Kerr black hole by Starobinsky, and then Tucholsky and Press and Tucholsky. And let me just say that for people that are not familiar with this, you can think about it as a rotational version of the Cherenkov radiation. It's a superluminal motion. Okay, so that's a basic phenomena. It's well known for more than 50 years. And what I want to do next is to describe basically all the main results. Well, the main result is a phase diagram. I want to draw a phase diagram of the solutions to the Tucholsky equation. And then we'll break it down, and I'll explain everything. But let me reveal all the main results. And this phase diagram is spanned by two continuous parameters. A, which is the angular momentum of the black hole, and well, usually we call it the spin parameter, but I don't want to mix it with the spin of the perturbation, so let me just call it the angular momentum. And omega is the frequency of the perturbation. And so those are the two continuous parameters in the Tucholsky equation. Well, in addition to the Schwarzschild mass, but the Schwarzschild mass will only set the overall scale, and there are also three integers, the spin of the perturbation and the spherical modes. But otherwise, the two continuous parameters are those. And I will try these two parameters by different combinations. The first is the Hawking temperature, and the second one is this combination that I defined here, A times omega, and which I will call G. So I can try the angular momentum for the Hawking temperature. For example, at extremality, the Hawking temperature is 0. And regarding this combination, for now, let me just say that it's a choice that I make, and I'm allowed to make this choice. I can span and describe the phase space using any combination of these parameters that I want, and we'll see the importance of that. But anyone that worked on this problem recognizes this combination right away. Okay, so here it is. That's the main result that I want to explain. A phase diagram of solutions to the Tucholsky equation. So again, this is the Hawking temperature. This is 0 here, extremality. This is the point where the angular momentum goes to 0, above which we don't have superradiance anymore. This is the variable that I defined as G, A times omega. And the region here in orange is the superradiance region. We can think about it as the analog of the long-range ordered phase in many-body systems or in quantum field theory. So that's the analog of a ferromagnetic or superconducting phase. So that's not new. I just drew the superradiance region. There is a sharp transition between the superradiance phase and the standard phase, which is the analog of a second-order phase transition. Okay, so that's just standard. Now, at 0 temperature, something very interesting happens at the superradiant bound. So, in this G variable, the superradiant bound at 0 temperature happens when G is equal to m over 2, where m is the azimuthal number of the perturbation.
Can you remind me, what is G?
G is A times omega.
Okay, thank you.
So something very special happens at 0 temperature and exactly at the superradiant bound. And what I will show is that at this point, there is a conformal symmetry emerging. It will emerge rather indirectly, and I will explain, I will be very precise, but nevertheless, it will be there. And that alone is not terribly surprising. People that worked on this problem might have anticipated that, although it wasn't. I think it wasn't made precise in the literature, but it's not shocking. The more interesting result that I want to show is that above this critical point, at non-zero temperatures, despite the fact that the symmetry will be broken, there is a wide region in which the physics is controlled by critical fluctuations, despite the fact that the symmetry is broken. And in this region, the physics will completely depend on a set of critical exponents that characterize this critical point. In this sense, the physics in this region is universal. And it extends to finite and high temperatures. Okay, that will be the main message. And this picture is reminiscent of the phase structure that we see in quantum many-body systems. Okay, so here this is the Bible of this field. And yeah, so people might have seen it in the context of condensed matter, a similar phase diagram, and I will show that it also appears in the phase space of solutions to the Tukolsky equation. So let me make a few more remarks. First of all, the shape that we see here is dictated by the scaling behavior around the critical point. So in condensed matter, different systems will have a different scaling behavior that will dictate a different shape for the critical region. That's one remark. The second remark is that, I just want to emphasize that the importance of the critical region is twofold. The first is that the physics here is universal, but more importantly is that it extends to high temperatures, finite and high temperatures. And this is crucial because if the physics was universal only, let's say, around the critical point, then it's not very important for experiment. But the fact that it extends to high temperatures means that we can actually probe it. And this is why people in condensed matter are very interested in this kind of system. Okay? So I didn't explain that, but that's just, that will be the result, and we are going to break it down and explain everything. But before I can continue, any questions? Yeah, okay. So that's by far the most technical slide that I have. Just spell out the Tukolsky equation explicitly, and the details are not important, but let me emphasize a few important things. So first of all, the separability into radial and angular equations. X here is the radial, is some definition of the radial coordinate. And as I mentioned, it is solved by it is separable and solved by the method of separation of variables. So the two equations share a separation constant A. As I mentioned previously, it is described by two continuous parameters: the Hawking temperature, which here is scaled with the mass to a combination that I call tau, and the variable A times omega, which I call G. And the radial equation depends on both of them. Now, very interestingly, the angular equation depends only on a single parameter, only on the combination G. And this is, of course, a well-known result. But it hasn't been used much. And what I'm going to show today is that it has a dramatic consequence. The fact that the angular equation depends only on one of the parameters will have dramatic consequences. And as far as I understand, there is no reason why it should have been this way. There is no reason why the angular equation should depend only on one out of the two parameters. But the fact that it does puts severe constraints. In particular, it implies that the separation constant is a function only of this variable. Again, this is a technical result. It's well known. And also the solutions to the spherical equation, which are called the spin-weighted spheroidal harmonics, depends only on this combination. And let me redefine the separation constant and define this combination. The reason is that this is the combination that is going to appear in solutions. Okay, but so from here on, I'm going to refer to the separation constant as beta, but it's nothing but a definition of this separation constant. Okay, so from here on, beta of G will be the separation constant. Okay. So let me start by discussing the critical point at zero temperature, zero black hole temperature. So this is zero temperature and exactly at the superradiant bound, and we call the separation constant at this point beta C. And as you mentioned before, there are some. At this point, the radial-Tukolsky equation, which is the own equation, reduces into the confluent hypergeometric equation and can be solved exactly. And we know everything about this function. This is well known since the original works of Starobinsky and Tukolsky and Tukolsky. And this is the conformal hypergeometric function is an int for conformal symmetry. Let me show you how exactly. So I think some people know this, but let me just make it precise. We can write the radial Tukolsky equation in this form with an operator that I call the L0, which takes this explicit form, and which is part of a symmetry group, an algebra, SO2, 1 algebra, using these two operators. It is also isomorphic to SL2R. And the Casimir operator of this group is related to this beta C, the separation constant at the critical point. Now, at this point, it still doesn't mean much. It still cannot claim that it represents any symmetry. Anyone can spot why? Well, the reason is that this operator is not Hermitian. There is an ion. So solutions to this equation do not sit in irreducible, unitary irreducible representation of this group. So at this point, it doesn't mean much. However, it is possible to associate, we can associate meaning to it by analytically continuing the space-time signature, for example, to Euclidean or to Kleinian signature, in which case this GC goes to minus IGC. And, well, anyway, this operator will become Hermitian, so in a different space-time signature, the symmetry can be realized. But I don't want to do that, and this is why I didn't put it on the slides. I just want to say that we can realize the symmetry by a weak rotation. And let me also mention that this is exactly the conformal ladder symmetry that appears in the case of the hydrogen atom. Okay, so strictly speaking, there is no symmetry for Lorentzian Kerr, but it appears indirectly in this way. And what I want to, what I will show is that, okay, we can realize this symmetry in different space-time signature, and there will be some pattern of symmetry breaking appearing as we move away from the critical point. And what I claim is that in Lorentzian signature we don't have this symmetry, but the constraints of symmetry breaking will remain. Okay, that's a claim, and I'm going to show that. Any question? So let me emphasize it. In this talk, I'm only interested in Lorentzian real-world Kerr. I will never analytically continue the signature, but just for the sake of the argument. It gives me a reason to call this point critical point. And let me also mention that this ladder symmetry that appears indirectly at the Kerr critical point is part of a much larger symmetry group of a different configuration, which is called a self-dual black hole, in which the symmetry is exact everywhere. And in fact, it's part of a much larger symmetry group, the full symmetry group, the hydrogen atom. So it can be viewed as a remnant, maybe even a remnant of a remnant of this much larger symmetry group. But I can say more about it later. So that's a critical point, and what I want to do now is to go a little bit away from the critical point by taking tau to be, or temperature to be small, and keeping this ratio fixed. So I will call this region around the critical point the scaling region. It was studied by these people, although it wasn't called scaling and it wasn't realized as a critical point. But essentially, they found that they can first Starobinsky and then Tukolsky. They found that they can solve the equation in this fashion by taking tau to be small and keeping this ratio fixed. Okay, so they found this scaling behavior, and by taking this scaling behavior, we can solve the equation perturbatively. So again, at this point, we can solve exactly, and once we go away from this point, we cannot solve exactly, but we can solve perturbatively, and this is done using a method which is called a match asymptotic expansion. It's a very common method that I think many people in the audience are familiar with, but let me review briefly. So what we can do, we cannot solve exactly everywhere once we are once we left the critical point, but we can solve in two separate regions, in the near horizon region and in the far region. And if the temperature is small enough, these two regions will overlap and we can match the two solutions. So boundary conditions are imposed at the horizon. Observables are measured at infinity. And we need a way to transfer the information about the boundary conditions to infinity. And we can do that if there is a substantial overlap. And there is one only when tau is small. So this is how we solve this problem. And let me just briefly sketch how it's being done. So in the near horizon region, we choose one of the two solutions to the equation. It's the one that corresponds to an ingoing boundary condition, so we don't want anything coming from the black hole. At the far region, there are two solutions.
So this is similar to this leaking boundary condition
Yeah.
story? The same story?
Yeah, I mean,
Porphyria is throwing a thing.
yeah, I mean, leaking, I think, I refer to different things, but it's just the ingoing boundary conditions.
But how to make the matching between the two regimes?
Yeah, you match the two solutions. So in the region where they are both valid. Leaking, I think, can also refer to other things, so I'm not sure. But anyway, in the far region, there are two solutions with two coefficients, and by matching the two solutions, we fix these two coefficients, or more precisely, the ratio between them. Okay, so the ratio is given by this result. In condensed matter language, we can call it the susceptibility. It was also interpreted as the inverse Green's function of some conjectured dual theory. But anyway, the point here is that this ratio, this susceptibility, diverges at zero temperature with a rate that is determined by these coefficients beta c. Remember, this beta c was born as the separation constant at the critical point. But because now we see that it controls the divergence of the susceptibility, I will call it a critical exponent. Okay?
Any corrections to this or some other power of tau? Or?
Yeah. Yeah. And we'll mention corrections soon. So this is the result, and as a remark, as a curiosity, let me just say that the form of this susceptibility is very similar to the susceptibility of the 1+1 Ising chain in transverse field, and the same structure of gamma functions. So I just want to mention it as a curiosity. It's probably because of the symmetries, but I don't want to claim that I understand. It's just interesting that. Just an interesting. Yeah. Anyway. Just to show some explicit values for this for the critical exponent. So now I can interpret these coefficients as critical exponents, and they can be computed easily for different type of perturbations. There are some explicit values.
Why some are imaginary?
Yeah, there are some of them are imaginary. Well, for once, because beta was defined in this way, so it can be imaginary. But even A itself sometimes can be imaginary. And yeah, it's just the way it is. I mean, it was discussed in these papers.
Doesn't mean anything.
Yeah, I mean, I don't mean to say that there is some underlying model that is non. In that case, you would think that it's not unitary or something, right? But in this case, it's just a solution. And well, the observable intercept here is the scattering amplitude, which can be computed by the asymptotic form of the radial waveform. So there is an incoming and outgoing waves with different amplitudes, and they can be computed from the solution. So those are the coefficients, C plus and minus, and the amplitudes come with some coefficients that can be computed, and the result for the scattering amplitude, which is basically this ratio, is given in terms of the susceptibility and these factors. Okay, so those are all classic results. Now, let me push further, and what I want to do now is to use this scaling behavior as an organizing principle for writing, at least formally, the structure of the solution. Okay, so what I want to do now is to push further from the scaling region and write a formal expression for the solution as a perturbative series in tau. So in the far region, the two solutions will receive corrections with tau, and they can also be computed asymptotically. They will take the same form of incoming and outgoing waves with different coefficients that can be computed probably numerically, and those will put corrections into the amplitudes of the incoming and outgoing waves, corrections in tau. So we can do that order by order. And the problem is essentially factorized into two parts. The first part is computing the connection coefficients that carry the information about the boundary conditions. And the second part is computing these functions in the asymptotic form of the solution. And those functions will depend only on the kinematics of the far region. So they do not carry information about boundary conditions. So all in all, we can organize, we can write a formal expression for this for the scattering amplitude in this form, and we can separate the dependence on the kinematics of the far region from the dependence on the boundary conditions, which goes into the susceptibility. So just very generally, everything will depend on the two parameters that span the phase space, tau and eta. But more than that, they will also depend on a continuum of separation constants. Okay? It is buried here in the solution. There is a continuum of separation constant. And crucially, it depends only on this combination. It didn't have to be this way. It could have depended on the two, but it turns out to depend only on this combination. And that's very important. Let me make a remark that might seem trivial at this point, that in the scaling region, where tau is small, this dependence on continuum of separation constant reduces into a dependence on a single number per mode. Okay, so that's a huge reduction. I just want to emphasize it. More generally, it depends on all this information, but in the scaling region, it will reduce into a single number. So that's a huge reduction. And at this point, it seems trivial. But what I want to do now is to take a different limit, a limit in which tau is fixed, but eta is small. And in this limit, a similar reduction occurs for a very simple reason. Because we see from here that in this opposite limit, again, the separation constant reduces into a single number. And yeah, so in this limit, the kinematic functions, all the components of the solution, the kinematic functions, the susceptibility, everything, will only depend on the temperature on this set of critical exponents. So I really want to emphasize that this is a huge reduction from a continuum of functions to a single number per mode. And as a consequence, the scattering amplitude will also depend only on the temperature and on the critical exponents. Now everything here, all this function and essentially the scattering amplitudes can be computed from what I will call the reduced Tucholsky equation. So that will be the form of the equation in this region, in this approximation or region, or however we want to call it. I'll call it the critical region. So in the critical region, the Tucholsky equation reduces to this form. Now, the functional form here doesn't look particularly simple, but the crucial part is that it depends only on the critical exponents and not on the continuum of separation constants. And in turn, these functions can be computed numerically from this reduced to Kolsky equation. So let me summarize these results using this diagram that we saw earlier. So those are the boundaries of the critical region, and now we see why, because they appear exactly when eta is smaller than 1. So remember that this is the limit that I want to consider. So it defines the borders of this critical region. So that's a result of the scaling behavior that was discovered by Starobinsky and then Tucholsky. Okay, it's a direct result of the scaling behavior. And the importance of this critical region is that the scattering amplitude, the physics essentially is universal. It only depends on the critical exponents. It extends to finite temperatures. So in practice, this is extremality, right? This 0 temperature is extremality, and in practice, it will be out to get close or very close to extremality. But this region extends to finite temperature, which means finite angular momentum, finite and I.
Just a general question.
Yeah.
Instead of TH, you could have used 1 over R Schwarzschild, right? Because that's a parameter.
Yeah.
There is nothing quantum here because there is no
Yeah.
So
This is So I want to emphasize. All I'm doing is studying solutions of the Tucholsky equation.
yeah, so this is all classical. I mean,
Yeah.
you call it quantum critical, but it's not quantum.
Yeah, it's by analogy. I mean, you can also extend it to a quantum scattering, perhaps, but yeah, it appears
I
in
mean,
the classical.
study one quantum, but here it's
Yeah,
everything. I mean,
yeah.
H bar could be
Yeah,
1,
Yeah.
20.
Yeah, it's just a Tucholsky equation. Just Tucholsky equation. So so that's the analog of the quantum critical point, and that's the analog of the quantum critical region. Any more questions?
In principle, at least for s equals 0, there is another parameter which is the mass of the field, and we consider mass
Yeah,
of
so-
the other field. So
Yeah, I didn't study the mass, the effect of the mass. So here everything is massless. In the Tucholsky, all the perturbations are massless. Yeah.
So, but when you say that this extends to non-zero temperature, I mean, you extends to non-maximally spinning.
Yeah.
And in terms of numbers, how close do you have to be maximally spinning to be able to see some of these effects?
Well, the point is that you don't have to be close at all, because, so the critical region is essentially an approximation scheme, and it's approximation that becomes better and better at high temperatures.
So, you mean you can go to TH or 1 over R Schwarzschild to equal to infinity?
Well, so what happens here is that when angular momentum is 0, this phenomena ceases to exist. There's something similar in many body systems. Above some scale, corresponding to a lattice scale, then you lose all the structure. So,
I mean, you have a line that goes across this.
yeah. But you can be close. You can be anywhere here, as long as the angular momentum is non-zero. And in fact, it becomes better at low angular momentum.
But I saw 2 things. I saw eta in that cone, but also eta much less than 1. So in your experiment.
Yeah, so eta less than 1, so this is eta equal to 1 and minus 1. So this is the region. Now it's an approximation scheme. It will become exactly above the critical point. And as you go further, it will get
But
worse.
how close can you go to eta equals
Okay,
plus or
no,
minus
that's
1?
an approximation. So it's
So
up to
it will break down.
Yeah, it's up to your standards of how good.
So in reality, the region that you study is inside strictly, right, that cone. It doesn't extend to the boundary. I mean,
Well, it's an approximation. And that's well, well, it depends on your standards of what is small.
Well, I mean, I have very low standards, but typically when the expansion parameter is 1, I don't believe it.
No, but
I mean, the approximation becomes better on the
yeah.
But how, I mean,
what's
can we
the-
estimate how good it is, say, for eta equals 1/2 or 3/4? I mean, because you have a series, right?
Yeah.
And, with some, this series may have very big prefactors. So, do we know what is the radius of convergence?
No, I don't know.
For example, how it grows exponentially the error when it becomes close to the diagonal. How it, how increase the error?
Yeah, no, I didn't study the convergence of this. That's a good point. But the main point in this business is that it's an approximation that becomes better at high temperatures. That's the main message. So it's true that well, how good the approximation is as you get to this line, I can't tell you, but it will become better and better at high temperatures.
So can you go to the point eta equals +1, th equal 1/8 pi m? I mean, can you use your approximation there?
Well, at this point, eta is equal to 1, and then it essentially breaks down.
Yeah, so there, if you want, at the point where it's at the best,
Yeah.
at 1/8 pi m, do you know what is the radius of convergence of your approximation?
I don't know the radius of convergence anywhere. I'm just saying that it's that as you go to I.
But how can you say that it gets better if you don't know the radius of convergence?
No, because it extends when eta equals. What I mean is that if you look at some value of g in condensed matter, that will be the coupling.
Yeah.
And you look at this value, as you increase the temperature, the approximation gets better.
You mean the eta becomes smaller at fixed g?
Yeah, that's what I mean. And in particular, this is not a sharp phase transition. In condensed matter, they call it a crossover. So what it means is that this is an approximation scheme and not, well, not a real phase, but an approximation scheme. Any more questions? So that's the main message, that in this region the physics is universal and extends to high temperature. So we can hope to measure it in experiment. If it was just close to extremality, then it would be hard. But since it extends to high temperatures, it might be possible.
Wait, but this governs, right, only a subset of the modes, right, with a particular, this governs only a subset of the modes with a very specific angular momentum or energy.
Yeah, it's this region, so it doesn't cover the entire phase space.
But do you know, like, are you going to be able to isolate that
From experiment?
from other things, or, yeah?
Yeah, I don't know, but I didn't compare it to experiments, so I don't know. But everything is of order 1, so it's not like a small 10 to minus 15 corner of the parameter space. Everything is order 1. I cannot tell you like what the experiment covers here or what it will cover in the future because I didn't run the analysis. But hopefully, if the experiment will eventually cover an order 1 region of the phase space, hopefully it will over. But I don't know. But the message is that it's really order 1. It's not like a tiny effect. Let me say just a word about how we could.
Sorry, but can you maybe go back not to the formulas, to the expansion actually? The expansion of your solutions in terms of this parameter.
Yeah, that's just a formal. That's just a formal.
So, but if you don't know what are the corrections, right? So maybe let me put it this way. This is Monica's question, a follow-up. F0, so the approximation could become bad for a fixed tau, right? When, say, F1 becomes large compared to F0, right? You have an expansion in tau. I mean, the radius of convergence depends on the coefficients that multiply the powers of tau, right?
Yeah.
How do these coefficients depend on angular momentum, on L and M, right, for a fixed?
Yeah, it's for every spherical mode.
Yeah.
I suppressed here the spherical modes, so this is
So for each spherical mode there is a different F1, F2, etc.
Yeah.
Is it some?
Well, I mean, no. F is the radial component, but there
Is
will
it?
also be, but things will depend on. Yeah. on the
So
spherical
basically,
modes.
if you see only a finite region of the sky, right? You receive a signal only on Earth.
Yeah.
Then you will have to sum over all the L and all the M, right? I mean, you'll have to find a solution that
Yeah.
depends on theta and phi, not
Yeah.
on the L and M,
Yeah.
right? Could that create a problem in the sense that could you have high L and high M components of the signal that you see in a given point for which the approximation breaks down?
Well, in general, the leading angular components are contribute more. I mean, that's the waveform receive, and people try to measure, right, the quasi-normal modes.
So you say that the leading components are low L, basically,
Yeah, I mean that's
at large distance.
I'm not saying yeah. But that's standard. But hopefully, I mean, what I'm saying is that okay, you can run the same analysis, but what I'm suggesting is that in this region, the analysis may be simplified because it will depend only on a set of critical exponents. And let me say a word about how we could hope to relate it to experiments. So, well, if we had a black hole in the lab, we can just scatter and measure the scattering amplitude, but we don't. Well, in this works by Misha Ivanov and Zhu and Saket, they showed how the relation between the scattering amplitude and tidal effects. Okay, so the scattering amplitude measures tidal effects, and tidal effects are in turn constrained by experiment. Just to give some examples of paper to do that. So, so I'm not saying that it's direct. There is still some gap between the result that I showed and that, but that's a possible way to connect it to experiment. Again, the scattering amplitude measures the tidal effects, which are constrained by experiment. And let me end by saying that, okay, now we can add it to the list. And a picture that people like to draw in condensed matter is with this magnifying glass, in which a critical region is magnifying glass on the critical point. And the same way we can think about this critical region as a magnifying glass for physics of extremal black holes. Let me also say a final word about a more general paradigm that emerges here. So in the previous work with Alfredo Guevara, which I did not discuss today, but I just mentioned, we show that a different configuration, scattering from a different configuration, which is called the self-dual black hole, is actually exactly mapped into the problem of the hydrogen atom. And today I showed you that Kerr black hole shows a behavior that is reminiscent of quantum matter, or quantum many-body systems. So
minus the H bar, right?
Yeah. No, I mean, yeah, it's not. I don't mean to say anything beyond what I said, just properties of the Tukowski equation. But nevertheless, I mean, this is mapped to the hydrogen atom, and that shows properties of many-body systems. So, yeah. Yeah, so I can't help by saying the word microstates, although obviously it's. I don't mean to say more than that, but what I mean to say is that this configuration, which is by the way not realistic, but this configuration seems in this way to be the fundamental configuration in which we can solve exactly.
So the self-dual is like a tau knot?
Self-dual tau knot.
Okay.
And yeah, so that seems to be the analog of the fundamental configuration, or the integrable configuration, or the integrable sector. We can think about this as the integrable sector of the scattering problem. And this configuration seems to be the analog of a composite system. So yeah, of course I don't know how to realize the microstates, but one possible realization of this is using scattering amplitude. So one possible idea is that the Kerr scattering amplitude might be we might be able to reconstruct the Kerr scattering amplitude from the fundamental building block of a scattering amplitude from this configuration, which we can compute exactly. So that's one possible idea. There are a few more ideas, but let me just say that for me the most exciting thing would be to try to measure the critical exponents. And another thing that I would be really interested in is to compute self-force corrections in the critical region. So what I did is only in the probe limit, but we can compute self-force or back reaction to this, which are also very important. And I expect that the analysis will be simplified in the critical region. I don't know how much simpler, but well, the problem is simpler, so I suspect that it can end in this direction. And let me end here.
Well, if I understand correctly, you've shown some relations between what you have here on the left side and the right side based on former developments, mathematical developments. Now, if we don't look at the mathematical developments, is there any way of guessing why there should be any correspondence between something that is strictly classical and something that is quantum?
Yeah, I don't know. I also don't mean to say anything about it. I just mean to say that Kerr shows properties that are reminiscent of quantum composite systems. But I don't mean to say anything more than that.
So you mentioned this, writing the Kerr scattering amplitude in terms of this circular. Does it have anything to do with the double copy formalism?
That's a great question. I don't know, but maybe. Yeah.
Can you comment on the relation of your generators of SO21 to the other SL2Rs that have been found? Like you
yeah, it's different. It's not the same.
You know it's different.
Yeah, there are many SL2Rs in this business, right? There are many SL2Rs. This SL2R is so first of all, it's not a deformorphism. It's a symmetry of the equation of motion. So many times people ask me about near horizon symmetries. It's not that.
Mm-hmm.
It's not completely unrelated because everything is Kerr, so I don't know if there might be a relation, but it's not that. It's also not anything of the law of symmetries of Sergei and others because it's not at zero energy. It's just the symmetry at this point. Again, this confluent hypergeometric was known since this works, so it's in this sense, that's why I said it's not shocking. I mean, Andy, for example, always says that these confluent hypergeometrics are in for conformal symmetry. So, but it's just that this was not written explicitly in the literature. The important point is that. So again, in Lorentzian, strictly speaking, in Lorentzian signature, the symmetry is not there. But the constraints of the breaking on solutions are still there, even in Lorentzian.
By that you mean if you have a solution and then you act with one of these generators, it's like imaginary in some way that's not allowed or something like that?
Yeah, so the critical point. Yeah, so the symmetry is not realized, but the pattern of symmetry breaking still constrains the physics, even in Lorentzian signature. That's the message.
It's a bit reminiscent to the walking phenomena, where you don't have a cycloidal phase transition if you remain in the real coupling space, but there's a complex fixed point. And the behavior of the CFT and the complex fixed point actually tells you about the behavior in the real coupling space.
Mm-hmm.
It's a little bit reminiscent of that. And this self-dual solution that you talked about is somehow analog of this complex CFT.
Yeah, so, yes.
That has the symmetry.
Yeah, you can think about it as a
require you to
right,
continue
right.
GC to imaginary.
Right. But we can also analytically continue the space-time signature, and then it's real. It's not complex. Exactly.
Does anything interesting happen to the entropy of this?
That's a good question. I don't know. Like, another way to phrase it is, the entropy and
At the critical point.
At the critical point.
Mm-hmm.
Yeah, I don't know. It's a good question. Another question that I thought about is like, to what degree this phase transition can be realized as a second order phase transition? Or is it just an analogy? I haven't seen a discussion about that, but it's interesting.
So this behavior near the critical point, you could, I mean, Starobinsky, Trotowski company could have discovered it by brute force, right, by doing an expansion in powers of this.
Well, they did.
Right?
They discovered this scaling law.
So they discovered this.
Yeah.
So the new thing is, what is the new result here?
The new result is the critical, is this. To take the opposite limit. And so, really I want to emphasize that this allows us to place or to associate Kerr to some universality class. That's the main message. To universality class such that if we can probe this universality class in experiment and match it to the one of Kerr, we can conclude that we observe Kerr. That's like the goal or the message. And if we see that a different universality class, we can conclude that we observe a different object.
Talking of which, can you extend what you did to Carl Newman, for instance? I mean, it's not that particularly relevant for nature, but just
that would be interesting to see the different universality classes. But what I'm thinking is more in line and like, okay, we want to verify that what we see is Kerr. It could be something else. It could also be a different object in GR. Could be a different object in a different theory. And who knows how many different universality classes there can be. That's the first one, but in condensed matter we have many, so I'm just inspired by that. Yeah.
Just to make sure I understood correctly, when you talk about tidal effects, those are effects on the space-time metric. Those are not effects where matter is moving around.
Yeah, we can measure it using gravitational waves. Not only, we can also study scalar and electromagnetic waves, but in practice, it will be, I refer to the gravitational waves that are emitted from the binary network. Yeah.
Thank you.